What? Oh.
They want it on the left.
This left?
Yes.
Okay.
You're speaking to that?
So you can speak to that slide.
Oh, okay. Fair enough. Okay, what is this?
Put it in your pocket.
Oh, okay, I don't have a pocket. Okay, thank you. Good afternoon. So my job is to keep you awake for Hugh. So I'll do my best. Let's see, what am I doing here? How do I advance? Okay, there we go. Okay, thanks. So, okay.
Right and left buttons.
Okay, that right. I'm sorry, you know it's a little late in the afternoon. Good afternoon. I'm very happy today to share with you some of the work that we're supporting in the low density materials program. This program is about 4.5 years old, and so am I in this program, about 4.5 years old here at AFOSR. So you'll see some of the products of the people that came before me, and then some of the things that we've been able to initiate since I've been here. So it's very clear why a program like low density materials is important in the Air Force. You know, many of our missions have, you know, structural platforms and components and systems that have to rise above the ground. And whenever you have to do that, you have to be concerned about the weight, and, you know, material density becomes very important in those applications. And it impacts everything. It impacts things like your capacity that you can carry on a mission, the range, the cost, mission performance, things like agility and survivability, and then of course environmental impact in the form of emissions and the like. So material density is important. This program really supports transformative research that targets advanced materials to enable reductions in weight of aerospace platforms and systems with enhancements in performance and function. And so I like to kind of think of this program in the terms of it being one that focuses on enhancing the specific capabilities for these aerospace systems. And so looking overall at improving the performance of per pound in the systems. And so sometimes that's a very explicit thing. For instance, like in lightweighting technologies where you're really just kind of taking weight out of the system, that enhanced specific capability becomes explicit. Sometimes it's a little less explicit in that we're working on really kind of far out technologies that we believe ultimately will lead us towards having some of these performance per pound enhancements in the materials. So some of the areas that we work are, of course, looking at new material synthesis and also advanced material processing capabilities. I think processing is really important because, you know, as we've seen in this couple of decades where we've been able to make different forms of carbon. Depending on how you process it, you can get everything from graphite to, you know, nanotubes to graphene and the like. And so that's an important aspect of what we're doing. We're looking at systems including composites, hybrid materials, nanostructured, and then anytime you're looking at things like hybrids, you have to be concerned about interfacial phenomena. And so there's some work in this area, and then of course multi-scale, both modeling and characterization is a component in this program. So I kind of like to keep things simple, and so this is kind of like the simplest explanation for the research thrust that I have. And the first is, I call it structural lightweighting, and simply put, that means taking the weight out of traditional composites. And I'll go into a little bit more detail about each of these thrust areas as I progress in the talk, but this is just kind of giving you the big picture of what these areas are. Second is on developing nanostructured hybrid materials. And by this, I kind of mean, you know, bottoms-up materials design, incorporating what is needed to get you the performance and the properties that you need for any given application. And that's a real challenging thing to do. Thirdly, the area of multifunctional materials, where we're looking at reducing system weight by designing the materials to do more. And so this is coupling structure and function. And I think I'll mention now that Dr. Leslie earlier this morning talked a lot about multifunctionality, and his program is really more looking at integrating multifunctionality into some of these structural materials. Here we're looking at basically at the material level design. So it might be materials that would ultimately feed and support a program like Dr. Lee's and others. Before I go into some of the accomplishments in the program, as I think others have mentioned, this has been a SAB, or Scientific Advisory Board, year for us. And so I put in this to kind of talk a little bit about some of the guiding considerations that have been used in terms of formulating what we fund in developing this program. And the first is, we've looked at tackling kind of broad-based challenge areas in a lot of these topics that can offer high payoff for future aerospace structures. And when you do that, looking at more broad-based challenges, sometimes it's necessary to have more collaborative projects where you give a little bit more interdisciplinary nature, even at the single grant level. And I find that having multiple PIs in some cases on a single grant provides that added forcing function for, in terms of students being exchanged between PIs, putting their final reports together and things of that nature, presentations and publishing together, really forces out some nice synergy in terms of the outcome that you get when you have a couple of PIs sometimes on a grant. Sometimes that synergy comes from having experimentalists teamed with theorists or doing more computational research. So you'll see projects like that. Of course, we all look towards establishing and stimulating research connections with the technical directorate. So in many cases, we have, in particular, young faculty that I really encourage to talk to the labs in terms of some of the applications and get a better understanding of what the Air Force needs are. And then leveraging of the services and other interagency collaborative opportunities. I'll talk a little bit more about that. International collaboration in areas that are appropriate. And also, as Dr. Lee just emphasizing, taking promising areas of basic researching, trying to leverage and push those towards more maturation by programs like the STTR and the Mantech program at Wright-Patterson, which is the Mantech program on moving manufacturing left, which is a new initiative there. Okay. I won't belabor this slide. I think I'll just point out the fact that in terms of international collaborations, on the starting, let's see, the 25th through 7th of this month, we'll have our first U.S.-India tunable materials technical exchange meeting at Wright-Patterson. And this, again, is one of those areas where we want to try to forge more international collaboration, because where that's appropriate is when you have areas of mutual strength from both sides. And after a lot of canvassing in the community, we believe this is a good area to target. And so that meeting will take place later this month. So now I'd like to talk a little bit about what I think are some of the overarching materials challenges, or an overarching materials challenge in the area that I really take into consideration in terms of developing what gets funded in this portfolio. And that challenge is related to the fact that the cycle time for developing new materials is quite long relative to the demand for new materials in aerospace and other industries. And so, and as an example, if we look at polymer, the area of polymer matrix composites, from this typical S-curve type configuration, looking at performance or properties as a function of time. It took us in excess of 30 years to conceive and develop and then ultimately mature polymer matrix composite materials to the point where now they're somewhat applicable in very risk-averse applications like commercial aviation. That took 30 plus years. And in some sense, polymer matrix composites are what I kind of want to say simple materials in that, these have two constituents. You have carbon fiber and a polymer matrix material. They're macro scale processed, in the bulk, and these are primarily optimized for their mechanical performance and properties. In contrast to that, I think the materials that we're really starting and the demand is for now are what I call nanostructured hybrid materials. And these are materials that I think are becoming increasingly complex. They have, in contrast to matrix composites, n number of constituents, and those constituents may be over several material classes. You may have metals, polymers, ceramics, etc. They can be processed over n dimensions, starting at nanoscale, nanophase processing, all the way up through bulk scale processing. And of course, these materials are now going to have to be optimized over for a range of properties, everything from mechanical to electrical, thermal, optical, and understanding how those properties vary as a function of time is critical for many of the applications that we need. So the two challenges really are that we have this increasing need for increased material complexity, and also a need to really do that a lot faster and understand it faster. And so in particular in the second thrust, we'll talk a little bit more about that. So now more details on the thrust and highlighting of some of the research in these areas. The first I mentioned is structural lightweighting, which is taking the weight out of traditional polymers. And some of the challenges that we address in this area are shown here. One is, how do you improve the specific properties in these materials? And so looking at things like increasing the strength and the toughness, or the thermal oxidative stability, kinetic stability, those kinds of things in polymer composite type materials is one of the areas. Another is looking at porosity in materials. So we have some work on air gels and other porous structures, and understanding how we can take weight out by putting in, having more porosity without compromising or having too big a trade-offs in terms of some of the mechanical and other properties. And then lastly is this area that I call multi-scale modeling of material degradation mechanisms. And this is really understanding material degradation as a function of time. And I mentioned we need to do that with the complex materials. We also need to do that with composites, because if we can do that, understand how these materials age from a fundamental material level, how that affects as you build up into the structure, then we can minimize some of the over-design that we currently have in composites. And that'll save weight. Okay, excuse me. Pardon me. Okay, so this is one of those broad-based areas that I mentioned that we've been working in. This is on, I like to say, cultivating breakthroughs in structural fibers. Some of the work funded here began about a decade ago, really, under Dr. Charles Lee, when this program was a part of the Polymer Matrix Composites program before it was brought into low-density materials. But anyway, the first effort is work of Dr. Satish Kumar at Georgia Tech, where he looked at doping polyacrylonitrile, PAN fibers. PAN is the high-performance polymer fiber precursor, and doping that with carbon nanotubes. And that templating with carbon nanotubes combined with other innovations like his bicomponent spinning process and increasing the purity and the molecular weight in these materials led to this templated, highly graphitic ordered morphology in terms of a pan carbon nanotube doped fiber, which led to real large enhancements in mechanical properties, approximately 50% enhancements in both the strength and the modulus in these materials. So this was a real significant advancement. This work ended a couple of years ago, but it has resulted in technology transfer to DARPA for their, as a part of their Advanced Structural Fibers program, where they've invested several $1 million to scale up this process and to advance on the properties further. Another really interesting innovation where we're really making strides in terms of improving carbon fibers has been in making carbon nanotube fibers. And this work was led by Matteo Pasquale from Rice University. And this program ended just last year. But in this here, Matteo came up with a way to solubilize using chlorosulfonic acid the carbon nanotubes and developed the process for spinning wholly nanotube fibers. So these are not dope fibers, these are nanotubes, nanotube fibers. And what's really nice about these fibers is they have significant advantages in terms of multifunctionality. The mechanical properties are nice, but you see here, if you look at the specific thermal conductivity versus electrical conductivity, these materials excel in both arenas. And so you have something with the electrical conductivity on the order of traditional metals, and also very nice high thermal conductivity. And so you can see these might be useful in aerospace structures where you really want to make sure that you can get the heat out of these types of structures. These are typically we would use something like this GF, which is a pitch-based fiber, is the highest thermal conductivity materials, but they've been able to make these, and this has resulted in a nice tech transfer where a company by the name of Teijin Aramids has picked up this technology and is scaling these fibers up. Okay, more recently, two other innovations in the area of structural fibers have been, again, the work of Dr. Kumar from Georgia Tech, where he's looking at making porous channel fibers. And so we call this a honeycomb configuration fiber. The objective here is to really decrease the density in these fibers. He's been able to get fibers on the order of 1.1 grams per centimeter, which is getting close to the density of water, so you can make floatable type structures with fibers like this. And so he's been able to process these using, again, his bicomponent spinning process with a sacrificial polymer layer that you can burn out in the carbonization, graphitization steps and end up with these nice channels in the fiber. And so you can imagine, I've shown the prettiest example of one of these fibers, but you can imagine over the years the challenges associated with getting these really nice 2-micron diameter channels in this fiber have been immense, and so they've done some really nice work to overcome those, and this work is now of interest to the fiber industry. And then lastly, I want to highlight work that's relatively new. It's been underway for about a year or so now, and that's work on developing nanofibers using electrospinning. And this is an example where one of the teams, interdisciplinary type teams, came to me with the idea of making a wholly polyimic composite structure. It's a pretty far out idea that needed engineering capability for electrospinning fibers, but it also needed new innovations in terms of synthesis, making new polyimide-based resins that you could spin and make the fibers out of and then consolidate into composites. And so we have two chemists here working with the engineer, Nebraska, Uris Zenas, to make these fibers. And what has resulted here, okay, there we go. It's really pretty. I didn't even want to clutter this with any data, because this is a picture that was selected as one of Nature 365 Days Images of the Year last year, and it's what it is 100 to 200 range nanometer electrospun fibers. And these are fibers of PAN, polyacrylonitrile. And these fibers, what's really interesting and surprising about these is they're not only very strong fibers, but they're also very tough fibers. And so if you look at this Ashby plot, which is kind of an eye chart here, so I don't expect you to pay attention to everything on here, but kind of populates all of the different types of fibers, including down here commercial polyacrylonitrile fibers, spider silk, which Dr. DeLong loves. Up here, everything to something like Kevlar. And the trend you see is that as you get really strong fibers, they're less and less tough, and so the stronger you get, they tend to be more brittle, and so the data kind of goes in this direction. But this arrow here shows the work of, or the data for these electrospun polyacrylonitrile fibers, where for increasingly small diameter fibers, you see both an increase in the strength of the fibers and an increase in the toughness of the fibers. And so this was kind of an unexpected thing. You know, as I mentioned earlier, the real goal here was to make polyimide fibers, but they started out with polyacrylonitrile fibers and have found these interesting things. And now we're looking more at understanding what's going on in terms of the orientation and the crystallinity that develops in these materials as you electrospin that can indicate or yield these types of properties. And so you see here in the data toughness, modulus, and strength, you see like this exponential increase in those properties as fiber diameter decreases. Okay, so that's kind of a highlight on some of what I think really nice cutting edge things that have happened over the past decade in this program on fibers. Now, here's work that we're doing on polymer films, and really trying to understand the morphology, control the morphology, and create, based on how we process the materials, create unique and exceptional properties. This work has been done at Princeton University by Professor Rodney Priestley. Dr. Priestley was a YIP winner, a recipient for my program in 2011, and I was very happy to see that he won the Presidential Early Career Award this past year. And so what he's doing at Princeton is employing a maple-assisted pulse laser evaporation system. Did I say maple? I meant matrix-assisted. The abbreviation, the acronym for all of that is called MAPLE. And MAPLE is a process that's kind of analogous to pulse laser deposition, except that in pulse laser deposition you have a solid target. Here in the MAPLE, the target is a frozen solution of a dilute polymer in a highly volatile solvent. And so when the incident laser beam hits that, you create a plume that has this highly volatile solvent that kind of just evaporates off, and then you end up with a very thin layer that you can kind of begin to control the thickness and, you know, a lot of the properties of this thin polymer on the substrate. And so Rodney is using this method to really study and control polymer morphology, the polymer formation and morphology formation in these polymers. And so, you know, this here is just one example of how you can control any of the parameters here, target concentration, and create a very large range in terms of the morphologies that you get and this so-called nanoglobule formulation that you get, which leads to drastically different properties in these materials. And so he's been able to show by using this technique in a very controlled way, you can make materials with significantly improved thermal stability, decreased density, increased mechanical properties and the like. And so it's a real, you know, basic research problem where we're trying to understand that, in this case, processing structure, morphology, property type relationships. Okay, last in the thrust one, I mentioned we're doing work on modeling to understand how at the molecular level, like at the atomic level, how these things evolve and degrade over time, to understand ultimately how that affects the structure and the degradation of the structure. And so here's work from a range of PIs. I'm not going to go into any specifics, but they're looking at everything from physical aging in systems to chain scission and how that propagates up into the structure, and thermal oxidative stability and the like, and how those affect the ultimate polymer properties. Ooh, 10 minutes. Okay, second thrust, bottoms-up materials design, hybrid materials. Here, some of the challenges are the synthesis and modeling control of 2D and 3D nanoscale heterostructures. Also, translation of the nanoscale properties to the macro scale, and then lastly, interfacial coupling. Okay, this is an area that I think is one of the bigger challenges for in the area of making structural materials, and that is the whole issue of scaling, nano to macro scaling of mechanical properties. We've been able to scale, in some cases, some of the transport properties like conductivity, electrical and thermal conductivity. But when you go from something like a soot, a carbon nanotube, and you try to scale the mechanical properties up so you can put them on something like a vehicle, the scaling has failed in us miserably. And so a couple of years ago, we worked with NASA to form a memorandum agreement to work this challenge together. We've put on the first of a couple of workshops, and have a coordinated group where we're looking at developing a roadmap and sorting through the fundamental challenges to begin to be able to make this translation from nano to macro scaling of mechanical properties. And this is a group of some of the researchers that are working this area. They're looking at how can we start to build covalent connectivity from these nanostructures. How can you build up and make macro structures? And so this team, Taronis and Ben Wang at Georgia Tech and Florida State, Richard Yang and Jacobson at Rice, I shouldn't say all these names, but they are looking at a range of mechanisms to establish some connectivity to build up macro structures. And so these are both theoretical and, in some cases, experimental approaches, things like nano welding with metallic components, metallic-induced nano welding, or electron beam radiation. And so this team is looking at that. And this is also related to MURI that we established, started in 2012, for nanofabrication of 3D structures. And the whole idea in both of these cases is to really look at how do you make these covalent junctions between building blocks to build up to structures. How do we characterize the junctions and then come up with scalable processes for making 3D solids. And there are significant payoffs to be had in these areas. And so this is work that I kind of highlighted last year, but I wanted to update it. It's work where, from the MURI team, this is the case, we have two MURI teams working this, one from Rice University and one from Case Western Reserve University. Well, they're led out of those, but these are all multi-university, of course. But this is team James Tour and Boris and Ajayan at Rice University. And here, Tour has come up with a way to make graphene on just about any substrate from just about any carbon source. And I think even Dr. Lee showed us a couple of years ago he was making graphene out of Girl Scout cookies. So he's been able to do that, but then he's come up with a clever approach using electron beam and alumina and the iron catalyst, here it is, iron catalyst, to actually grow carbon nanotubes on that graphene substrate. And Boris has done the theoretical predictions to show that you should have these 7-member rings at the base of these structures, and if you do, you should have the seamless contact, and they've done the measurements to show that you do get ohmic contact, so you have these really nice covalently bonded structures. Again, this is at the nanoscale, so this is like a image 10 micron scale bar here. But this is a nanostructure, and so the idea is, can we make larger macro structures? And so this is an example where they use this same technique, except that now instead of a copper substrate, they started with these nickel porous network, almost like sponges of sorts. And this is where Ajayan took the work in making these type structures onto a macro scale type device. And so you have nano fabrication on a macro scale substrate, and they're beginning to evaluate some of the properties that this type of buildup and configuration hierarchy can give you. And so this is just an example of them, of them looking at the emission properties of these types of materials, the graphene nanotubes on a nickel, and showing that here you have a very, very quick current uptake or onset with these types of materials. And this is really just the beginning. They're beginning to characterize some of these materials and take it to the next level. Okay, 4 minutes. Okay, so the next area I mentioned is interfaces, and this is work Professor Marilyn Minus at Northeastern University is doing, where she is looking at studying the interfacial interactions, in this case between, again, polyacrylonitrile, which is really important in terms of fibers and other high-performance polymer systems, and that interaction between that and something like carbon nanotubes. And so she's looking at, you have a pan just kind of clumped on a carbon nanotube surface, all the way up in terms of dispersion to something like pan that is confined between exfoliated plates of carbon nanotube, and looking at this interaction energy between these and correlating that with experimental data. And so when you have something where you have very poor interaction between the nanotube and the polymer, you get properties like this, where you get burnout, holes, just not very good integrity and correspondingly low mechanical properties. But if you can get really good dispersion quality, that correlates with very nice properties after you take it through the process of graphitization. And so this, I think, is very important work, because it will allow us to begin to quantify the quality of dispersion and ultimately relate that to properties that you could get from materials like this. I think I'm going to go a little quicker, down to 2 minutes. So this is the last thing I want to highlight in this area, and it's an interagency collaboration that we recently initiated with the National Science Foundation on looking at 2D materials beyond graphene. And so several of my colleagues have talked about this area, but I wanted to mention that this is a new initiative that the program is involved in, and there will be funding along with the National Science Foundation, and again working with Dr. Masoom Ma internationally, and Gernot Pomeranki here to fund projects in this area. Okay, the third thrust for the program is on multifunctional materials, and this is coupling structure and function. And so here we're looking at new materials to help engender improve multifunctionality into load-bearing materials. And so I don't have a lot of details here because I knew I didn't have time, but we're looking at things like boron nitride nanotubes, which are great for neutron shielding. And so looking at how to make boron nitride nanotube composites, nanocellulosic crystals, which are both optical and radio transparent. And so this whole area of cellulosic materials at the nanoscale and the outstanding properties that you can see there, these are all components within this phase of the work. And then also another challenge that we're looking at is materials and methods for enabling active, adaptive, tunable, efficient performance. A lot of words, but the major thrust that we're doing there is, again, another interagency collaboration on origami design for engineering systems. And I believe Dr. Stargell gave a really nice overview of this work on Monday, and it's one of the areas that we're jointly working with the National Science Foundation. But what we've done is funded, I think this is wrong, it shouldn't be 8 grants, but 12 grants to the tune of in excess of $26 million in an AFOSR lab test in this area. And what was exciting about this area is that Rich Vaya at Wright-Patterson initially contacted me and said this was a great area, something they had not thought about, but they would be very interested in forming a team to work the area. And so they have formed a cross-directorate team that's working this particular area. Rich and Tim White are doing things that are more aligned with my portfolio in terms of developing materials that you can indeed fold and make some of these folded structures that are of interest to the Air Force. And then the team from the Aerospace Systems Directorate are more aligned with Dr. Stargell's portfolio on integrating these types of materials into structures. I think I'll end now and just summarize by reiterating that the program is looking at enabling weight reductions and with enhancements in performance and function, and our thrust, structural lightweighting, nanostructured hybrids, and multifunctional materials. And we've done a lot of work, again, to forge some collaborative teams to look at really broad-based challenges and working very closely with other agencies and the other services to advance some of these objectives. So I'd be happy to answer any questions you have at this time.
Okay, do we have any questions? Yes.
Real quick, great brief. Thank you.
Oh, thanks.
I'm curious what your engagement with all of the OSTP centers of excellence. I know Air Force has one.
Yeah.
So you've never mentioned any of that. Is that because it's not an AFOSR area, or?
Yeah. Okay. So in particular, we've engaged with the additive manufacturing center that OSTP formulated, and that one is kind of being sponsored or led out of Wright-Patterson. Jennifer Fielding is in charge of that. And so that initiative that I mentioned earlier, moving manufacturing left out of Mantech, it's loosely related to that. And so we are loosely engaged, and we're actually bringing on a couple of projects related to additive manufacturing based on some of the work that's being done there. So yes, we have engaged on the OSTP initiatives.
Yeah, it looked like the functional material piece, where you have the blending of materials, and all be a great place for the additive and a phenomenal 6-1 research area.
Totally agree with you there, and that's exactly what we're targeting. I just did the work to fund a young investigator program in that area specifically.
Any final question? No? All right, let's thank our speaker. So I guess next up is me.
Should you want me to mic you?
But I need the